start the official recording so that YouTubers can learn about homework as well. So how's homework going, folks? Good enough. It's due tomorrow night. So now is the point where perhaps you have started, hopefully. Perhaps. I don't think that this homework will take as long as the first one, but I could be wrong about that. As usual, it depends on how facile you are with the material. I did want to go over a couple things that have been common points of questions or confusion that hopefully can prevent some confusion from the folks who haven't gotten to that point. But are there any specific questions that anyone wants to throw out before I do that? Those of you who are working on it, who have started, I should say, haven't finished. Zoomers, anything from y'all? No? Okay, would you like to talk about it? Would that be helpful? Oh, not as many nods as I would have thought. Okay. I can eject. So in terms of things that I've had questions about, so the story problem from this homework, of course, is near and dear to our heart. You're predicting the probability that someone's getting a job offer based on their number of publications, number of posters, and extent of their quantitative training. So the first section is asking for 2 predictors to be added for number of publications and number of posters. And the last 2 questions I've gotten a number of inquiries about. Enter the slope difference in logits for the number of posters versus number of publications. Now, this is not a question that you've seen an example of, but I guarantee you know how to do this. You're asking for a computation using the fixed effects. So this is a linear combination. You're asking for a difference in the 2 slopes. There is an order of operations here, though, that's important. You have to find the slope difference in logits first, and then convert that slope difference to an odds ratio. You cannot take the difference in the odds directly. It will not give you the right answer. So this is an example of using a linear combination through the GLHT option if you're using R. This is a LinCom statement in Stata. And then you would have to exponentiate that slope difference to get the odds ratio. There is code in the example 2A to do all of that. If you can't find the particular piece of code or it's not working, get your calculator out. E to the answer. The E function is the exponentiation function. Another question that I've had is about the third model. Let's see here. So section 2 is adding in controlling for quantitative training, where there are 3 categories, low, medium, or high. You were instructed to make low the reference group and to use indicator dummy coding, I believe. So then there's a number of inquiries about the slope and logits for low versus medium. It's the slope and logits for medium versus high, low versus medium, etc. So the tricky part for these is figuring out which ones are in the model and which ones are not. As a general principle, if you're using indicator dummy coding, anything involving the reference group is in the model somewhere. It's only the questions that involve alternative group comparisons that you need to write extra code for. So low versus medium, it's in there. Low versus high, it's in there. Medium versus high, not in there. But this is an example of when you would do a coding combination where the first entry is given a -1 and the second one is given a 1. That's how you make a difference. And the order matters. The p-value would be the same either way, but the direction of the difference needs the -1 to be first and the 1 to be second. In section 3, this is an interaction model. So the extent to which the effect of number of publication depends on quantitative training. Is your publication history as important if you have high training as if you have medium training as if you have low? That's the idea here. So I had questions from folks trying to figure out some of the simple slopes. So for instance, the simple slope in logits for the number of publications at low training. The model would look like this. I don't think I'm giving anything away by writing out the equation. The words and the instructions tell you what it should look like. So section 3 would look like this. I have an intercept. I have what I would call main effect slopes for n pubs. I have a marginal main effect for n posters because it's not interacting with anything. My 2 dummy codes from before, don't forget those when you add in your interactions, they stay. And then the 2 interaction terms. So given these interactions, low versus medium and low versus high, who is this the slope for number of publications? For whom?
Low.
This is for low because of the way I set up the coding. How would I get it for another group? 3-step process, right? Step 1 is what? How do I figure out the ingredients needed to make a simple slope when there's an interaction term in a model? Step 1 is what?
The things that have the thing you're looking for.
Yes, pull out the things that have the thing. That is correct. So pull out the terms that have the slope in question. We'll start putting some nouns in there, although the thing that has the thing works for me as well. So I need, since I'm talking about the slope of publications, right, I need that. So I need that. What else do I need? Does npubs show up anywhere else in my model? I need these 2, right? Okay, that's step 1. What's next? Factor. Factor the slope that these are for. So let's get rid of that, get rid of that, get rid of that. Let's add some brackety things. There. Step 3, what's left out in front, that's your linear combination. So these are the ingredients that you would feed into a lincom or our GLHT. Then I also asked for slope differences among these groups. So here is a trick. I'm going to copy this, save this. Somehow I ended up with extra lines. Okay. So in terms of, this is the general equation. I'm going to keep this one right here. If I'm filling this in for low, what goes here? In terms of like what I would enter into my GLHT, like set of zeros and ones, or the multiplications of the variables for the lincom. I need a 1 here. I need at least 1 beta 1. If it's for low, then what goes here?
For low?
For low, a 0. Yeah. So there is, let me put this back in for a second and make it look like it's the same structure. I'll put that in. Basically the 1 is implicit because there's nothing multiplying it, okay? So that's for low. Why does it do that? Go back to the middle. What if I want to do it for medium? Same thing, right? I need a 1. What goes here?
1.
What goes here?
0.
Okay. What if I want to do it for high? Getting good at this, right? A 1? 0 on that one. And here? 1. Cool. All right. So it is not a coincidence that I ask you for what the simple slope is before I ask you for what the differences between them are. Because guess what? If you figure out what it is, the differences is literally subtracting your code. Before I get to that, though, question from the Zoomers. Are we supposed to see the screen? Yes! What an excellent question. Okay. It's on YouTube, though. My sincerest apologies, Zoomers. The first class, I forgot they had a quiz. This class I forget to screen share. Like, we haven't been living with Zoom for 3 years now. My sincerest apologies. This is where I'm at. So I wrote out the model for section 3, extracted what we need to figure out the simple slope of publications, and now I'm working through what it would be for each group. So we have then group differences potentially, right? So what if I said low versus medium? Let me get that one. Come down further. Low versus medium would look like this. Put a minus sign in there. And low. There we go. So low versus medium is medium minus low. What's 1 minus 1? What's 1 minus 0? What's 0 minus 0? Okay. That's your ingredients to find the slope difference. If you know what it is for each, you can literally subtract your lines of code from each other. But now that we have the result here, did I even need to do this? Low versus medium is one term in the model. It is what beta 5 means. What if I did low versus high, in which case it would look like that. Put high here. 1 minus 1, still 0. 0 minus 0, still 0, not 10. 1 minus 0. Okay, did I need to do this? No. This is what beta 6 means. How about medium versus high? Do I need to do it? Yeah, because it's not involving the reference group, but I'm not going to do it. You're going to do it. Because I know that you can subtract 1s and 0s. Once you get to this level, though, like, honestly, I will always do this. I will ask for something, and then I will ask for the differences, because you have the ingredients if you found the somethings first. Then you find the odds ratios. So find the differences first, then take the odds ratio of the difference. All right. Sorry, Zoomers, for leaving you out for the first couple minutes here, but hopefully we can catch up with the logic. So are there questions on this? All right. Then another last thing that I've answered several questions about, predicted probabilities. So there are 2 ways to do this. And I realize that I can't spell probability, but it's close enough. Probability. That's yet another inverse link function. I'll teach you that one later. There's probability and there's probability. The easy way to do this is to use either margins in Stata or prediction in R and ask for the predictions for these levels of your predictors. And it's type equals response in the prediction function, which is the inverse link, the probability. If you want to do this the harder way, you can write out a lincom in Stata or a GLHT in R. So if I, for instance, if I want to do the first one, the predicted probability, go back to my document here, back to the top of the model. Probability of a job offer given 2 publications, 3 posters, I think it is, and low quant training. So I would fill in 2 there, 3 there. What goes here? 0 and 0. And that means that these things would all be zeros as well. Just get rid of that, get rid of that. Here's what folks are forgetting, though, when they build statements with this. Beta 0. The intercept always goes into predicted outcomes because there's an implicit not variable here that's always there. So if you're not getting the right answers, make sure you have your intercept in your prediction. The intercept doesn't go into anything involving a slope, though. It only goes in when you're creating a predicted outcome. Okay. I think that's all the main questions that I've been answering. I have office hours tomorrow if anyone wants to talk to me. Otherwise, email, screenshots are okay as well. Yeah, I think those are the only main questions I've seen repeatedly. Any other things you want to talk about? The next homework is not yet available. It will be available probably the beginning of next week. It's not due until after spring break. But it's going to be on categorical and nominal, which is what we've been talking about now, and I promise there's no interaction terms in that one. Because trying to figure out what the hell y is enough. That's what we've been working on, is trying to figure out what is y in these models here. So should we do a little bit of reviewing? Yes. Okay, so the idea of categorical data, which involves ordinal, nominal, and then potentially some sort of partial credit. The difference is in the link function. The link function controls whether you have an ordering or not. If you have an ordering, then we're going to use a cumulative link function. Go back a minute. Cumulative logit is what it's called. There's also cumulative probit flavor or log flavor, whatever you want. But cumulative is the key phrase here. The way this link function works is that it takes all of your answer choices into account in every single submodel. You have C-1 submodels to model C possible categories. So if I have 4 possible categories, I need 3 submodels. And it's 0 versus 1, 2, 3 as a binary submodel where 1, 2, 3 is lumped together in the first one. 0 and 1 are lumped together, and 2 and 3 are lumped together in the second, and 0, 1, and 2 are lumped together in the third. So the first thing that we had to figure out using an empty model so that it can recreate the proportions of responses in each category exactly is which way the model is going. If the model returns the logit of the probability of the higher category, the blue, then what is that called? Intercept or threshold? That's an intercept, just like usual. So if it's predicting the logit of the probability of the higher of these choices, it's an intercept. If it's predicting the logit of the probability of the lower, what is that? Threshold. That's the cut thing in Stata. So you can't trust your software to label these things in a way that is necessarily correct or consistent. We got to figure it out ourselves. If I am given thresholds and I want intercepts instead, what can I do to fix it? Multiply it by -1, which I learned last year is called the additive inverse for math people. I did not know that was a thing. But yes, -1 times an intercept will give you the threshold. Do you remember why that is? The reason that it works that way is because logits and probits are symmetric. If I know that the logit of the probability of the higher category is 2.2, then I know that the logit for the probability of the lower category is -2.2. That's why. That's why it's -1. A logit of 0 corresponds to what in probability?
0.5.
Yeah, it's right in front of you. I often do that. I'm shameless about the audience participation. Yes, logit of 0 corresponds to a probability of 0.5. So if I have a positive predicted logit, I know it's somewhere above 0.5. If I have a negative predicted logit, I know it's somewhere below. What does a logit of 0 correspond to in odds? A 1. What's the smallest that an odds ratio can be in theory? 0. So you will never see a negative odds ratio. So keep that in mind when you're working through your homework too. Inside these story problems, I have your odds ratios. Do not look for minus signs to indicate negative slopes because they're not there. If I have a negative slope, what is that going to be in odds ratios?
Less than 1.
Yeah, 0 to 1. If I have a positive slope, it's 1 to positive infinity. Yep. So it's asymmetric in odds. It's symmetric in logits. So the cumulative link function is what we're dealing with. It's also known as proportional odds because even though we allow different thresholds or intercepts for each of the submodels, by default it constrains the slopes to be the same. We don't have to live with that though, and that's where we left off, the exciting conclusion of do my slopes need to be different across submodels? What's my conditional distribution for this model? I'm not saying my residuals are normal. What am I saying they are? Starts with an M. Yeah, multinomial distribution for these. So whether it's ordinal or nominal, it's still the multinomial distribution underneath it. The multinomial is basically like Bernoulli, but for more than 2 categories. Doesn't have a variance. So that's why these equations don't have residual variances in them. Residuals, I should say, because there's no separate variance. Nope, that's not what I want. This is what I want. Okay, how are we doing? Thumbs up? I was hoping for sideways. I'll take up. Hooray. Do you want to go back over empty model? Would that help? Yes? Strong nod, you win. So the data we're playing with, 3 category outcome. How likely are you to apply to graduate school, where 0 is not likely, 1 is and 2 is very likely. So I'm treating this as ordinal in this model. I know that 0.55 is the proportion of people who answered 0, 0.35 is the proportion of people who answered 1, and 0.1 is the proportion of people who answered 2. That's going to tell me what my model is giving me, knowing that column right there. So the 2 submodels that I'm going to be building, written technically like this, the outcome that I'm predicting in submodel 1 is the log of the odds of the probability of answering 1 or 2 instead of 0. So the higher in this submodel is 1 or 2 instead of 0. I'm going to abbreviate that like this, logit of apply greater than 0. The second submodel, the log of the odds of the probability of answering 2, instead of 0 or 1, or logit greater than 1. The output that I got from this process, so I'm using GoLogit2 in StatF to start with, a logit coefficient of -0.2 corresponds in probability to a, let me find it, probability of 0.45. So here's the R output that goes with it, and I fixed it, by the way. This was wrong on the first version of the handout, and I figured out why. So I corrected it down here, but I have a note. In my R code, I had accidentally put false here. I think I was testing to make sure that I knew what it was doing, and the probabilities that it spit out were exactly backwards. So I fixed it in this handout, and it's all internally consistent now. So the R code to go with this is VGLM is a function inside a new package called VGAM. All of the packages that I use are, of course, inside the electronic materials. Reverse equals true. It means give me intercepts, damn it. I hate thresholds. Parallel equals true means proportional odds force all my slopes to be the same for now. So in logits, the intercept for submodel predicting an answer greater than 0 is -0.02. That corresponds to a probability of 0.45. Likewise, the second submodel predicting an answer of 2 rather than 0 or 1 is a logit of -2.2. That corresponds to a probability of 0.1. So getting your predicted logits, converting them into probabilities will tell you which way your model's going. If these were thresholds instead, what would this number be right here? if it gave me thresholds instead? What would this be instead of -2?
2.
Positive 2. And then a positive 2 would convert into a probability of 0.9 instead of 0.1. So it's the opposite, 1 minus the predicted probability. Okay. We did this model, I think. Would be helpful to go back over it a little bit. Let's pick the GPA. I like that one. Let's see. Let's do the R output. So GPA has a significantly positive slope. It's 0.6 in logits. So for every unit higher GPA, my predicted logit of the higher category goes up by 0.6. Is it the higher category of a 2 or the higher category of a 1 or a 2? Both. Or yes. That's the way I phrased it last time. So when you only see one slope, that's a giveaway that this is a proportional odds model. It is not differentiating which submodel you're in. It's the same slope across them. So the change in the predicted logit doesn't care what the predicted logit is about. Only the intercept differs across submodels in this. We can say more generally that people with higher GPAs are more likely to apply to graduate school. I can say that. People whose parents went to graduate school are more likely to apply to graduate school. People who went to private university, not necessarily more likely, non-significant. Positive coefficient, though. All right. Likelihood ratio test against the empty model to see if this model is significant. Yes, indeed it was. Here's my odds ratios. Let's see. Yeah. This is doing it by hand. So this code should work for everybody. Odds ratio is a column and then adding the confidence intervals defaulting to 95% here. And I think this is where we left off. Does that sound about right? Okay. Any that you want to hear again or differently? Okay, we're going to fit next up then, brand new stuff, starting on page 5. This is called a non-proportional model, non-proportional odds model. And the difference in the notation, how do I know that this is a non-proportional odds model? What has changed? Louder. I'm hearing people muttering. Be emphatic.
So on the slopes, you have like, all of the slopes are different from each other, basically. Like if you look between the models, it's
Yep.
10 and 11, so they're not the same between the models.
Yep, so this is beta 1, but now I have a second subscript differentiating whether it's predicting greater than 0 or greater than 1. That's my notation scheme here. Notation is always author specific, so there's not a universal way of writing these things. But showing an equation can help readers who don't want to see your words more quickly to understand what you're doing. So your readers are going to come in 2 categories. There's going to be, like my husband, words, words, words. Just show me the equation already. And then there's going to be equation, equation, equation. What the hell does this mean? Give me some words. Right? You have both kinds that you have to talk to. So the words I would use is say I'm using the first subscript indicates which predictor it is, the second subscript indicates which submodel I'm talking about. And I would introduce the term submodel because that's my way of thinking about it. So the difference in the code then to do this, I've taken off the option PL, so I think it defaults in Go Logit 2 to this model. I've added a super cool option called gamma, though, which doesn't mean anything in relation to what other gamma abbreviations would mean, but it's an option that allows us to directly test proportional odds, which is super cool. The data likelihood ratio test has a 6 in parentheses now. That's because I have 6 slopes in my model. I have separate slopes for each predictor in each submodel. So if I look, say, at GPA, the coefficient is about 0.6. So the logit of the probability of answering greater than 0, that's what this submodel means, goes up by 0.6 for every unit GPA, and that is significant. In comparison, the logit of the probability of answering something greater than 1, which can only be 2 given this coding scheme, goes up by 0.7 for every unit of GPA. Now, do you think that 0.7 and 0.6 are different? Well, it looks like one's bigger, but can I just say, yeah, it's numerically bigger? No, I can't say that because I got to take into account how precisely each of these is estimated. Does it surprise you how different the standard errors are? No. Why are they so different?
Because we have fewer people.
There's only 10% of my sample who answered a 2. So I have much less precision with which to judge the slope. It would fluctuate more across samples. But whoever wrote GoLogit 2 knew I was going to ask that question. And this gamma option produces this alternative version of the table where I get whatever the slope is in the first submodel and the difference in the slopes directly. Very cool. So the way that I would interpret this gamma 2 number here is that the slope of GPA is more positive in the submodel predicting 2 by 0.12 than it is in the submodel predicting 1 or 2. But if I look at the p-value, it's not significantly more positive. So it's numerically more positive, but not distinguishable statistically. The only one that looks like it might be different is for private, which is actually in an opposite direction. So there is a non-significantly positive effect of going to private school on your decision to go to graduate school of a 1 or a 2. There is a almost, or this is a, that slope I would say is less positive heading into negative. It's almost a difference. The slope itself is negative. So up here tells me what the slopes are in each submodel. Down here, this box tells me if they're different. Given that I only have 2 submodels, there's only one possibility for the difference. But the more submodels you have, the more possibilities there are for how the slopes could vary across the submodels. Yes?
So then, to tell if you would use the p-value as your guide in order to tell if they are violating like that proportional assumption, basically.
Yes, so this is close to violating it. But here's the thing. It looks like if we let it be separate, neither one of these is actually significant. So they're different from each other, but neither one of them is far enough away from 0 for me to say that this has an impact on your likelihood of applying to graduate school. But certainly if I had a slope in one direction in one submodel and in an opposite direction in another, I'd want to know that, because that would potentially wash out in some sort of weighted average. So if we compare it, it's 0.23 or negative 0.53. If we go back to what it was in the previous model, it is 0.05. So the 0 slope in the previous model is a weighted combination of what they would be in each separate model. So this 0 slope doesn't really characterize anybody, per se. So when I found this, I was really happy, because this made this like, oh, this is really easy. In R, you got to work a little harder. So here's the same model in R. There's only one thing different in the code. Can you find it? Yep, that's it, as indicated by the box here. Parallel equals false. Means just let it be whatever. So now we have the coefficients differentiated by submodel. So this is telling you directly what the slope is in each submodel. I've labeled these out here for us. What it doesn't tell you directly is whether they're different. How am I going to solve that problem? Linear combinations. So what you're saying is I needed to take one slope and subtract the other. If only I knew how to do that. See, now you understand why I'm drilling you on the slope differences concept, because it keeps showing up in a lot of different contexts. We know how to do that. So I can do a couple of other things here too. In Stata, I also did a likelihood ratio test. I don't think you've seen an example of this yet, have you? This kind? Nope. Okay, I'll do both. So what I had to do is first go back to the proportional odds model and store the results of it. So there's a line of code that does that. I didn't print it on here because it doesn't generate any output. Store the results of my non-proportional odds model, and then there's a new command called LR test, that stands for likelihood ratio test. We list the model that has more parameters first and the model that has fewer second, as indicated by my note here. So I can do a likelihood ratio test as to if I let the slopes be different across submodels, does that make my data taller? Does that make my model stronger? So I can compare my model with only 3 slopes to the model with 6, 1 for each submodel. And the results of this give you, it says LR chi2 3. What that means in English, likelihood ratio chi-square. So this is being treated as a chi-square test statistic. 4.01 is your test statistic. 3 is the difference between models in the number of parameters, and that's your degrees of freedom. So I added 3 slopes because I let my 3 slopes differ across the 2 submodels. That's what this means. The probability that goes with that chi-square is 0.26. So what does that mean if it's not significant?
That there's not much of a difference between the 2 models, and you
Yep.
probably don't have like different slopes. Like you're not gaining anything by having the slopes be totally separate.
Yep. On the whole, like on the whole, the 3 slopes, letting them be different did not improve my model significantly. So the way that I would talk about this is that my model fits not better. No, seriously. When you add things, your choices are better or not better. If you add something and it doesn't help, it's not better. You didn't make it worse, it's just not better. If you take things away, so if I started with a non-proportional odds model and I simplified, then your choices are worse or not worse. So I can say it either way. The model where the slopes get to differ across submodels is not better than the one where they're constrained to be the same. Or I can say the one where they're constrained to be the same is not worse than the one where they get to be different. So this can be confusing given that Stata prints a likelihood ratio test. This one that shows up by default up here is a joint test of all the slopes that are in the model against an empty model with no slopes. So this is like, does my model predict this outcome at all, yes or no? This one is, does my model predict this outcome better after I put 3 new terms in it? No. So these are nested model comparisons. And I don't think I've taught a class in my career where I haven't had at least like one of these somewhere in the class, right? This morning we did, what, 7 of these? Or not this morning, earlier in the afternoon, I should say. It felt like the morning, but. So this is a very common thing. This idea of comparing the log likelihood of the model and then adding some stuff and seeing if it went up or if the -2 log likelihood went down, that's a very common thing across many different areas of statistics. In R, we can do that as well. So I did ANOVA, or ANODA, as I prefer to call it, because I have the proportional odds model and the non-proportional odds model, and in this one, the nested model has to go first. So it's backwards relative to what it is in Stata. But the chi-square, labeled here, deviance, is -2 log likelihood difference. That's my likelihood ratio test statistic, and there's the p-value, so they agree. So on the whole, it looks like the slopes are not different, but there's nothing in the R output that tests the difference between each one. So I'm going to do that. We're going to use our friend GLHT again. So the first 2 zeros are for my 2 intercepts. Here's my GPA slope test. Here's my parent degree slope test, and here is my private school slope test, -1 and 1. So it's the slope for the second submodel minus the slope for the first one. So then it's the order of first submodel versus second. So then I get differences in logits between the slopes, and I get the exact same answer with respect to the last one being almost different. Okay. So putting it all together then, individually, the only slope that looks like it might be different across submodels is this one. Collectively, the 3 of them, not different. Questions? So let's think about the scope of this example. I only have 3 predictors. How many submodels do I have? Just 2. What if I had a 5-point scale? How many submodels would I have? 4. How many possible ways could the slopes differ across submodels then? A lot. 6 per slope. If there's 4 possible slopes, there's 6 pairwise differences across them. Do you want to figure out by hand which one of these need to be different? I didn't think so. GoLogit 2 thought of that too. GlowLogit. I'm really good at typing today, my goodness. GlowLogit is the next edition of the package. It's coming soon. I have a beta release, No, just making shit up here. I can't type. GlowLogit 2 has an option to automate this. So in the online materials, I have those files where it figures out algorithmically which ones want to be different from each other, and you don't have to do it. It's beautiful. SAS Proc Logistic has that option, and I could not find anything common parallel in R. Not that it doesn't exist, but I couldn't find it. So the model that they came up with, not surprisingly, only the private slope gets to be different across the submodels, which is exactly what we found. Once you constrain the slopes of GPA and parent degree to be the same across submodels, then it turns out that that difference that was p-value of 0.058 is actually squeaks under 0.05. So the last one in the ordinal set here is what's known as a partial proportional odds, where some of them are different and some of them are the same. So in the Stata code, I specify with this little option here, NPL, that I only want the private slope to be different across the submodels, and the others are constrained to be the same. It still spits out the output in the same format, but now you can see the GPA slope is constrained across, the parent slope is constrained across, and the private is different. The gamma option still tests the differences. There's only one difference, and it has a p-value of 0.033. So yes, the slope of private wants to be different across submodels, but within each submodel, it's not significant in the first place. So I probably wouldn't keep it if I were building this model for the sake of anything other than a class. Here's my odds ratios. And in R, this little chunk right here. Not only does parallel equal false, I got false, squiggle, and then the name of the variable that I want the non-proportional odds for. So you can pick which ones you want to be different and which ones you want to be the same as the default. So now, the intercepts differ across submodels, the private slope differs across submodels, and the other two are constrained the same. And last but not least, here's my test of the difference between the private slopes, what I have to do myself in R, and odds ratios. Okay, not so bad, right? The trick with this is just figuring out what you're predicting. That's the hardest part. The rest of it follows once you figure that part out. Now, to make pictures or to do predicted probabilities is trickier with these models. In Stata, less tricky. So I have an example of what it would look like if I wanted to generate hypothetical people to make like a plot or something. So I'm asking for GPAs of -1 up to 1 in increments of 1, parent degree of 0 or 1, private of 0 or 1. Predict XB means give me the prediction in logits, but because no one knows what the hell a logit is, taking that off gives us probability T. I spelled it right there. In R, the prediction package does not work with VGLM, so I had to make a workaround. This is a method that I also have to use in SAS because I don't have an easy way to do it in SAS either. I call it the method of fake people. I am going to generate fake cases with every combination. I have 12 fake cases where I have the same combination of 3 levels of GPA, 2 levels of parent degree, and 2 levels of private school. So all possible combinations of 3 by 2 by 2. I am then creating a data frame with 3 columns, GPA 3, parent degree, and private, and I'm naming my data frame FP. Do you know what that stands for?
Fake people.
Fake people, yes. By the way, this is a technique that I use in SAS and SPSS anytime that I want to generate predicted values. I literally add fake people to my data set. Here's the trick. You don't give them a fake outcome. You give your fake people the prototypical values of the predictors that you want in your plot. So you don't have to go in and like look to see if anybody actually has every possible combination because they may not. So I'm adding, like, basically the idea is I would add 12 fake cases to my data set. Don't give them a fake outcome. I then re-estimate my final model on the data set with the fake people in it. Because they don't have outcomes, they don't screw up anything. They're not being used in estimating the model parameters. But every software package has an option to generate predicted outcomes and save them to your data set, and it will generate predicted outcomes for your real people and your fake people. So then you easily get a column that you can feed into Excel or whatever plotting package you like to use. So I do that in other packages that don't have easy sorts of margin things. I'm doing basically the same idea here, except I'm not re-estimating my model. I'm using a function within base R called predict. So here's the logic. I'm creating a new data frame that starts with my fake people in those 3 columns, okay? These are what my columns look like. I am then adding another column that I'm calling Y, and I'm saying build that column using the predict function from my final model, add it to the fake people here, type equals link. What do you think that's going to give me? Logits. So I don't have to say logit or probit specifically, because it knows based on the stored model object what my link function was. So link is what I write. So that's going to give me a predicted Y column in logits. The end result, though, is not going to be just 1 column, because the model gives me the predicted probability for every single possible answer category. So the end result down here is logit for greater than or equal to 0, or greater than or equal to 0. That can't be right. Yeah, I named it badly, but greater than 0. This should be a T, not equal to. There we go. Let's fix that real quick. Greater than 0 or greater than 1. Those are my logits. So the logits correspond to the submodels. They are lumping people together because that's how the submodels are specified. If you want to have probabilities, though, then we add another column. Y_prob is what I've named it, and that's type equals response. That's your inverse link. So it knows that the inverse link of logit is probability. You don't have to tell it. But fortunately, it figures out that what I'd actually like is the probability of each category. So I don't have to do anything extra other than rename the columns into something that's not terrible. So if I'm somebody who has a GPA of 2, my parents didn't go to graduate school and I went to public university. But my predicted logit from the submodel predicting greater than 0 is this number. My predicted logit from the submodel greater than 1 is this number. I can then work backwards to figure out what the predicted probability is for each of these categories. So my predicted probability of answering no is 0.76. My predicted probability of saying 0.17. And my predicted probability of very likely is 0.07. So these are the kinds of things that you can then plot, basically, for different kinds of people and show, like, as this variable goes up, they're more likely to shift from the high 0s over to the high 2s, that kind of thing. I made some pictures, and I did it in Excel so you could see the math and how I came up with this stuff. So the first submodel here, this is the logit of greater than 0, and this is the corresponding probability of greater than 0. So GPA is on the x-axis, and then I have different lines for different kinds of degrees and universities. These lines are all parallel, right? Couldn't we agree on that? This picture right here? Coincidence or consequence? Consequence. Why are these lines all parallel? No interactions in this model. So the effective GPA doesn't care what school you went to or what your parents did. The difference between the blue lines and the red lines illustrates the difference between parents who did not have a graduate degree and parents who did. The logit of answering above 0 is higher if your parents have a graduate degree. The blue lines are higher. The difference between solid and dashed of each color is illustrating the effect of public versus private, and they're very close together because that variable wasn't significant. I can take these predicted logits and turn them into predicted probabilities. E to the logit over 1 plus E to the logit. That's my inverse link. And these lines look a little bit bendy because probability has to shut off. So the model is predicting a linear slope of GPA in logits. That translates into a nonlinear slope the closer you get to 0 or 1. That's my first submodel. Here's my second. This is differentiating 0, 1 versus 2. So now I'm trying to predict who is really likely to go to graduate school. Well, first off, note the difference in the scale. The lines are down here. You're less likely to say, yes, I'm definitely going to graduate school across the board. It looks like there is a smaller effect of parent degree and a larger effect of school type. And the compression of these predictions as we get closer to 0 is illustrated much more in this bottom one here. So the bendy lines is a consequence of the inverse link function here. All right. How are we doing? Hanging in there? Feel like you could do this for real if you had to? Maybe? Guess what? You're going to find out in a couple weeks. All right. Do we have the strength to talk about nominal yet? No? Eh? You want to talk about something else instead? I've got a couple slides I can do instead. Effect sizes. We can talk about this one real quick, and then we can go home early. How about that? Oh, yes. Yes, yes, we can. Let me do the last two slides here, and then we'll do nominal next time. How's that sound? Okay. All right. So slide 29 in lecture 2 here, effect sizes. So we can still do odds ratios for ordinal models, the same as we did for binary models, because ordinal models have binary models as their base point. Pseudo R-square, though, is much trickier because you have to somehow aggregate across the submodels. There are examples in some of the readings, and you'll find these in the literature about ways that people build like cross-classification type tables. So for instance, they might have like the number of zeros and ones, and then like how many zeros and ones were predicted by your model, and they look at like how accurate you are. To me, that is trickier because at the end of the day, each person does not have a predicted 0 or 1. They have a predicted probability. And to me, it is unfair to say, well, my predicted probability is above 0.5, so I'm going to call that a predicted 1. And my predicted probability is below 0.5, I'm going to call that a predicted 0. Because what if you had somebody that was like 0.49 and 0.51, they get shoved into the ends of 0 and 1, versus like 0.9 and 0.1, right? Those are much closer to the endpoints. So I don't like the idea of collapsing or rounding your probabilities into zeros and ones because I feel like that loses a lot of the error of prediction and the precision. So here's what I would do instead if I wanted to do something like that. Instead of collapsing people into zeros and ones, I would use a random number generator, so such as built-in R. Stata has this, all statistical packages have this, where you can generate a random variable from a Bernoulli distribution, so a 0-1 distribution, and use the mean as their predicted probability. So then you're still allowing some capacity for error in that case. We can do the same thing if you have categorical data by drawing from a multinomial distribution. And then you could potentially fit some sort of correlation of your predicted outcome from that process with the real one. So the bottom line is that if you're going to try to do some sort of like how accurate is my model, I think that there has to be a way to represent the error of your prediction as part of that process rather than rounding into the zeros and ones. So it's trickier, but it's necessary. So here is a summary of how models for categorical outcomes differ from general linear models for continuous outcomes. What are we predicting? In ANOVA and regression, it's y. That's it. We have an identity link. Do you remember what that term means? Times 1. Yeah. So general linear models are a subset of generalized because of that. The link function is identity. Whereas in generalized models, we have a link function, such as logit, probit, etc., and we're transforming the predicted probability of either a 1 or a 0. What estimator and what conditional distribution are used? So we are using maximum likelihood now, where the model parameters are the ones that collectively make the data the tallest, and the search process tries out different values of those, checks the height, moves it accordingly, tries to make it taller, figures out where subsequent moves don't make it any taller and calls it done. That's convergence. That, in general linear models, the equivalent is actually something called residual maximum likelihood. And that is the same thing as ordinary least squares if you have complete data. So they don't tell you this, but actually you are using a type of likelihood estimation when you do regression in ANOVA. The conditional distribution is normal in general linear models, whereas it's Bernoulli if you have binary or multinomial if you have categorical. Because we have a normal distribution in general linear models, we have a separately estimated variance for the outcome. That separately estimated variance allows us a lot of choices in how to talk about effect size related to variance explained. So we can do R-squares for the model, we can do partial R-square, semi-partial R-squares, we can do all these kinds of things, we can standardize slopes. We don't really have that anymore. The lack of an estimated residual variance means that we don't have as many choices. So for effect sizes, it tends to be odds ratios for these models. The other thing that is tricky about this, a lot of times we fit alternative models and add stuff, and then we watch what happened to the stuff that was already there. Like, oh, my slope is 1. Now I added this other covariate and my slope became 0.8. That means it has a smaller effect now than it used to have after controlling for this other thing. In generalized models, we can't do that. Because the residual variance doesn't change, it's 3.29 if you're in logits, it's 1 in probits, the model changes scale as you add things. So the coefficients are not directly comparable across models. They are on different scales. The way that I can explain this is a quick analogy with department stores like Kohl's, which I shop at probably at least once a week online, and in which case, if you ever pay full price at Kohl's, you are doing it wrong, okay? You're doing it wrong. There's always Kohl's Cash, there's always sales, there's always something. So we know that if you're the manager at Kohl's, you know that that's how it works. So let's say that you want to sell a set of shirts, and in order to make your minimum, like to break even, the shirt needs to sell for $25. Let's say it's a really expensive Kohl's shirt. So what you do is you put $50 on the price tag, and then you say it's a 50% off sale. And if that doesn't work, and there's still a pile of shirts sitting there, you change the original price tag to $100, and then you say it's a 75% off sale, because it's still 25 at the end. That's how these models work. Like, in order for more variance to be explained, we have to sort of pretend like there was more in the first place in order to still end up with 3.29 when we're done. So think about like the original price tag changing every time you add predictors to like what the total variance must have been in order for you to end up at 3.29 by the time you're done. So there's more mathematical details. You can look this up. There's some articles that talk about this, but just as you can't directly compare the coefficients as you add things because the model's not on the same scale. So a little bit of complexity there. Okay, 309. We're still going to get done early. Questions? All right, then office hours are tomorrow. I hope to see folks Thursday. We'll do nominal, and I'll let you know if we have more material posted after that. So thanks for being here. Take care.